Hey guys, welcome back to another video. It's STEM Made Simple, and today I'm going to be telling you a different approach to graphing functions. In this way, that's actually the real way it's supposed to graph functions instead of plugging in points, which you've all been taught. This is a different way of thinking, and it's going to show you that you can graph faster, more efficiently, and you'll be able to understand graphs better than you ever have. So let's first start off with what a function is. So a function is just a principle that you have an input, and that input gives you an output. So you put something into something and you get an output. I like to think of it as a box. So you have a box here, the function machine. Call it f of x. It has a ejector here, and it has a injector here. So we plug in an x into the function box, spits out a y. Okay. So this box is called f. It gives you an x, you plug in an x, and you get a y. This is the principle that is called f of x. And you have f of x equals x squared. What this means, this parentheses in x, means that whatever you plug in into here, whatever input you plug in, the function, every function is different. Depending on the function that you have, it's going to transform that input and give you an output. It's a cause and effect. Okay? So anywhere you see an x, you can plug in a point. That's what it is. That's all function is. You have plug in an input and you get an output. The function connects the inputs and outputs. Okay? You plug in an input. You plug in something. You study. Okay? You study. You put in study time. You get a good grade in the test. You putting in study time, okay, outputted, the effect of that was you getting a good grade in the test. Anything in life can be described as a function. That's the principle that we're learning today. So how can you relate this back to transformations? You know what transformations are. They transform the function, transform the graph, because the graph shows what the function looks like, okay? So this is what a function looks like, the transformation, the equation. So it's y equals a times f times b times x minus h plus k. Okay. What do all of these variables mean? Okay. These are transformations we can apply. You have to remember, you have to know these. You have the vertical transformations, you have the horizontal transformations. These are what these describe. These branch off from the vertical transformations. You get addition and subtraction, addition / subtraction. Here you get multiplication / division. And it's the same thing with here. It's ditto, the same thing. Why did I say it like that? We can write this again. So say vertical transformations again. Vertical transformations, which these are things you know. We have the vertical stretch / compression, the vertical reflections, and vertical shifts. what do these stand for in our equation that we can talk about here, that we talked about? Well, the vertical stretch and compression is our A value. This value right here. Our vertical reflections is on the A value. It's this plus or minus right here, plus or minus. It can also be here, plus or minus. Okay, if it's minus, if plus stays the same, minus changes depending on what you do. The shifts is this right here, this positive. It's a K. Why I talk about addition and subtraction, multiplication, division? Because these two, with the method I'm talking about, you apply multiplication when you transform the base function, multiplication. With a shift, any sort of shift, horizontal shift, vertical shift, it's always an addition. Okay, slash subtraction. And with the horizontal transformations, H transformations, you have, again, you have a H stretch, horizontal stretch, slash compression. This one's a little annoying, but we can go over it. You have an H shift. This one's pretty easy, but also pretty annoying, but we can get over it. And then this is a H reflection. So let's go over it. So the function y and f of x are the same thing, but I prefer f of x. F of x makes more sense. If you have f of x equals x squared. This is the parent. This is what we call the parent function. The parent function is the parent. It literally dictates how a function looks like. Okay, x squared, the quadratic, looks something like this, a parabola. Okay. Now let's see, is it a function? Yeah, it's a function because it's f of x. If we also want to check, we can just do this vertical line test. If it goes through it once, it's a function, but I'll go over that in a different video. But all of these are functions, okay? I'm not going to trick you. All of these are functions in this video. So how can we build, this is approximation, how can we build an exact graph and get ordered pairs like x and y values for this? Well, we can make a point, or like a table. So we have f of x equals x squared. So let's plug in x's. So let's plug in the 1. So we have a 1, we plug in the 1, so it becomes f of 1 equals, now anything we say x, we plug it on a 1. 1 squared. 1 squared is 1, so that means our y value, because f of x means the function will produce a y value. Remember our machine, we get a 1. So at 1, we'll be at 1. So this is our ordered pair. 1, 1. So graph. So here x value is at 1. Y value at 1. We're at 1. Let's plug in a 2. F of 2 equals 2 squared. So we plug in a 2. We get a 4. 2, 3, 4. Let's try a negative 1. F of negative 1 equals negative 1 squared. So that means we get a 1. Let's try a 2. A negative 2 this time. Okay? F of negative 2 equals negative 2 squared. So at x equals negative 2, we're at, what do you think? Positive 4, because negative 2 squared is negative 2 times negative 2. Anytime you times a negative number by even amount of times by itself, you get a positive number. So, just like this, you have a visual of the graph. It's drawn to sketch, but this is how it looks like. the parent function, but we can add transformations to this. Usually, what happens is you don't have something like this all the time. You have transformations, and they aren't tricky at all. Like if I gave you something like f of x equals x squared plus 4, you'd recognize that this is a vertical shift. So any value we add, we just add 4 to it. But if I had something like f of x equals negative x minus 3 squared plus 2, how you do this? I mean, you could plug in points, but it's a lot of algebra. So, what is my method exactly? Well, let's try this one. So, I'm gonna assume you know vertex form. I'm gonna assume that you know everything, because this is not like a deep dive explanation. It's just a better way to think about it. You need some basic understanding to be able to do this method. But like I said, I'm gonna go over like a review. So let's try one. So let's try this value right here. So we're gonna graph this value. How can we graph this function? So what if we start off, instead of plugging in values, which we can do, plugging random x values, we can just get the parent function itself. So f of x equals x squared, because see the squared, that means it's a quadratic. Okay, that means we can start from there. Let's plug in points that we know. Okay, so we know negative 1 from before is going to give us a 1. Okay, a 1 is going to give us a 1. 2 points in the graph, that's all we need. Here's what's cool. Remember I told you about the multiplication and addition transformations? The ones, anything with reflection, with a stretch, is multiplication. Anything with a shift is a addition, something addition. We have to use PEMDAS. PMDAS. So it's parentheses first, exponents, multiplication, division, addition, subtraction. So why did I emphasize that? So to transform the graph, what the graph does is it applies PEMDAS, depending on what you do. So these MDAS are really important here, because since we have one multiplication transformation, this one being on the outside meaning that it's a vertical, it's a reflection, some sort of reflection. This is reflection about the x-axis. But we need to know that we can just apply it. We can see that if it's not on the x, that it's going to be on the y logically. So that means right away we could times everything in here, all our y values, by negative 1. Cool. Okay, what else can we do? Well, we have this vertical shift. So we can plus 2. Why am I doing like this? Because we have to follow order of operations. If I had plus 2 and then times negative 1, it wouldn't be correct. So you have to follow PEMDAS. So this thing requires you, this method requires you, well, for each graph, like some graphs like trig functions, logs, like they're the same method but a little more tricky. Not really though. Like for graphs like quadratics, cubics, square roots, if you know PEMDAS and you know just what these are, like what they do, like what if they affect the x or the y value, and what kind, if they're multiplication or addition transformations, you can just do this method. So right here, we applied the negative 1, the negative 1 to the y values, and we add the plus 2. What else we need to apply is, remember that when we shift to the right, or this is the horizontal shift, anything on the x plus or minus means we're shifting towards the right, correct? So that means we're going to add 3 to all of our x values. So let's compute some basic math over here. So this is going to be our transform function. And see how we derived it from the parent function. We can use with any graph of x squared. All we have to do is the parent function's graph, points, and what it looks like. Okay? So 3 plus negative 1, that's 2. 3 plus 1 is 4. Right now I'm just adding. Negative 1 times 1 is negative 1. Correct? So negative 1 times 1, this is for the y value, is negative 1. Plus 2 equals to 1. Correct? Negative 1 times 1 is, again, negative 1. Plus 2 is 1. Always quadratic because the y values are always symmetrical. So this is what our function looks like. So at x equals 2, we're at 1. And at x equals 4, we're also at 1. It's not right. 3 plus negative 1, let me make sure, 2. And then 3 plus 1 is 4, correct? And then negative 1 times negative 1 is negative 1 plus 2, that's 1. Okay, good. So this is what the graph looks like. 4, 1. Well, I think we need a I'm gonna try a. Oh yeah, this makes sense. Sorry if I made a mistake. Let's try something. Let's try another point. So I'm gonna try maybe a 2. 2 squared. Remember, f of f. This is just the parent function. So f of x equals x squared. So we plug in a 2 squared, a 2. We get a 4. And we change this, so we get x equals 5. Negative 1 times negative 4 is negative 4 plus 2. That's a negative 2. So right away I could tell that the graph sort of looks like something like this. The reason why it flips, this is a whole different like a whole different thing. But anyway, this is a transformed function, and this is the parent function. Okay, so all we did is we got the x values of the parent function, and we just transform them literally. We didn't have to plug in any points. Usually people plug in points, which is fine, but I feel like this is a better way. Well, now that I went over that explanation, isn't the best explanation, but at this point I'm assuming that you know about graphs, so I don't want to go a lot of depth into it because just the method itself. The method itself needs you to know a little about graphs, but if you want, I can make a more detailed video. So, yeah, that's the method. If you want me to show it with other graphs, functions, trig, log, rational, those I can do those as well. But yes, this is my first graphing video. I want to show that in the context of when I'm going to be graphing, why I'm not going to do f of 1, f of 2, f of 3, is because I'm doing this. Times I might, but for the most part, like I'm graphing trig functions, I'm not doing that. That's, first of all, trig functions are a whole different story, but yeah, I hope you enjoyed the video, and have a good day.